Alrighty, good morning, everyone. So unfortunately, this week we're going to have a couple people missing. So I'm going to have to record pretty much every day. And the microphone on my computer doesn't work. So that's why I'll be wearing these here. So I'm Bluetoothing to the computer. So that way I have an actual microphone so they can actually hear what I'm saying. So anyways, so I'm not here listening to music while actually talking to you. So, or talking to my wife or anything like that. So anyways, so that's kind of what's going to be happening for this week. Hopefully it'll only be for this week and then we won't have to do it after that. So it should be great. We have to improvise sometimes. All right, so some quick announcements. So exam 2 practice stuff is now posted. The homework associated with exam 2 is now posted as well. And don't forget, exam 2 is already Monday. Very quick. So having said that, we have started chapter 16. So chapter 16, just to remind you, so far we have done Coulomb's law. So we said Coulomb's law says that if I have two charged particles separated by some spatial distance of r, then the force on the first particle by the second particle is equal to, in magnitude anyways, the force on the second particle by the first particle, which is equal to k, where again, k is just some number. So just remind us, k is equal to 1/4 pi epsilon naught, which is equal to 9 times 10 to the 9th. This is a Newton meter squared per Coulomb squared, times the magnitude of Q1 times magnitude of Q2 divided by that distance from center to center r squared, where in this case, it's a little bit complicated in the fact that if I have like charges, whether they're both positive charges or both negative charges, doesn't matter as long as they're like charges, that manifests itself as a repulsive force. So these two forces are equal magnitude but opposite direction. So they're both being repelled. But if I have unlike charges, so for example, plus with minus or minus with plus, in that case, it has an attractive force. In that case, again, the two forces are equal magnitude but opposite directions, which satisfies Coulomb, or not Coulomb, so Newton's third law. Pardon me. So let's do another example. So last time we did one example. So let's do one more example. This one's a little more complicated because we have a little more geometry to talk about. I think Logan asked, how do we determine angles and all this different stuff? And we'll see that in this problem here. So we'll do one which has some geometry to it. And then we'll move on to start talking about electric fields. So here's the problem we're going to look at. So this says we have this beautiful configuration here. We have three charges. We have Q1, which is minus 86. Mu here, C means microcoulombs. So this is 10 to the minus 6 coulombs, that's what a micro means, which is on the x-axis. We have Q2, which is 50 microcoulombs positive, which is on the origin. And then some distance above that, 30 centimeters, we have Q3, which has 65 microcoulombs. And then we also know a bunch of distances. We know that this distance here is 30 centimeters. We know this distance here is 60 centimeters. We know this angle is 30 degrees, an angle theta. And finally, we know the bottom distance is 52 centimeters. So basically what it wants us to do is, as we talked about last time, if I have more than two charges, it wants us to use then superposition to then determine what is the total force on Q3 here. And just to remind you, what superposition says is that the force on the ith particle is then equal to the sum over j of then Fij, where I is not equal to j. So again, all this means is I'm going to calculate all the pairs of forces and then vector sum those together to then find the total force on each. Okay. So let's do this as an example and see how this goes. Beautiful announcements. So all I'm going to do first is I'm going to look at Q3 and I'm going to look at the forces by the other two particles onto Q3. So I'm going to look at the force on 3 by 1, force on 3 by 2. And first thing I'm going to do is I'm going to draw a free body diagram, which is the same thing we would draw in physics 175. But using the fact that now I have to look at the charges and say, are these attractive forces or are they repulsive forces based off of how these charges relate to each other? So let's start off with the force on 3 by 1. In this case, 3 is a positive charge, but 1 is a negative charge. So is that an attractive force or repulsive force? Attractive force. So in this case, what we know is that the force is along the line that connects the two charges together. So this is going to be my force F31. So it'll point down in this direction. Now, let's look at the force between 3 and 2. In this case, both 3 and 2 are positive charges. So is that a repulsive force or an attractive force? repulsive force. So in this case, along the line means it's going to be along the y-axis. So this is going to be my force F32. Is okay? Now, if I vector sum these two guys together, I could use the tip-to-tail method or the parallelogram method. But if I use the parallelogram method, all I'm going to do is project this guy here. I project this guy here, and then this would then be the sum force between the two of those. Right? If I use the parallelogram method. If I use the tip-to-tail method, I would just move this guy to here, and then this would be the force that connects. But ultimately, this is what F3 should look like. All right. Is okay with this? So now what I'm going to do is I'm going to break this thing up into what we would do in physics 175. I'm going to break it up into components and then look at the components and then calculate what's the net force on each one. So in this case, what I'm going to do is I'm actually going to move my origin from this location to this location, since what I'm interested in is this force. So I'm going to call this now my x-axis, and this continue to be my y-axis. So I'm just going to move my axis to put this guy at the origin. I can always do that. So good. So in this case, what I'm going to do then is what? I know these are parallel lines. So I know alternate interior angles are parallel lines based off of high school geometry are the same. So this angle is 30 degrees as well as this angle is 30 degrees. Everybody remember alternate interior angles of blah, blah, blah. Okay, great. So now what I'm going to do is I'm going to say, okay, what I want are the components of this guy, and what I have is a two-dimensional vector. Right? So what I'm going to do is I'm going to look at both the x direction and the y direction. So let's say I'm going to look at the x components of F3, and I'm going to look at the y components of F3. Now, according to superposition, what that means then is we're only going to look at the sum of all the forces acting in the x direction. So in this case, how many forces are acting in the x direction? So remember, this force here is made up of this force and this force. So which one of these forces has a component which is in the x direction? F31, right? So in this case, this is simply going to be what? F31, but the x component is F31. It's okay with us? Now, in the y direction, I want to look at how many of these forces are in the y direction. So how many forces do I have in the y direction? I got both. So I got F32, all of it or part of it. All of it. And is that positive or negative? Positive. Good. So I'm going to write this then as simply F32. Then I'm going to add on to that the components of F31, which is in the y direction. And is that guy going to be positive or negative? Negative. Good. So I'm going to write a negative F31 y component. Now, let's do the x component first. So according to this axis here, what I want is this portion of this force. So according to that, that is the adjacent side of this angle, and adjacent goes with what? Sine or cosine? So think of your SOHCAHTOA, right? So adjacent goes with which one? Sine or cosine? Cosine. So this is then going to be the same thing as what? F31 cosine of the angle of theta. Is okay? Now I'm going to apply Coulomb's law, which says that the force F31 is the same thing as K times the magnitude of Q3 times the magnitude of Q1, all divided by the distance between the two, where it's this distance of 67. Okay. So in this case, I'm going to write this as K, the magnitude of Q3 times the magnitude of Q1, all divided by 0.6 meters squared. Everybody's okay with this? Because look at my numbers, what I get in this case then is this works out to be about 121 newtons. This is my x component. Oh yeah, I forgot the right cosine. Sorry, thank you. Thanks, Logan. Now it's 121. There you go. Good. Now let's do the same thing for the y direction. So now I get F32 minus then F31. And if we use cosine here, then this has to be the sine component. And the other way I know that is because I want this portion of it, right? So I want this guy across here. And since this is the opposite side, this has to be the sine portion. Now, again, I'm just going to apply Coulomb's law. So this says that this is K times the magnitude of Q3 times the magnitude of Q2, all divided by the distance between those two, which in this case is 30 centimeters. So that's 0.3 meters squared, minus K times Q3 times Q1 magnitude, all divided by 0.6 meters squared times sine of theta. So again, wherever I have the F there, I'm just replacing Coulomb's law. So just using definition. Plugging my numbers in this case, this then works out to be 255 newtons. Now what I have are two components of a vector. So how do I have to represent a vector? Going back to 175, how do you represent a vector? What's that? Well, we have that, but now that I have those, remember, what do I need to fully specify? So I need the length of the vector. Exactly, and then I also need the angle, right? So we're gonna be looking for then is how long is this guy, which is what we call the magnitude, and then what is this angle that's called that angle theta 3. Good. So to do that, we're gonna use Pythagorean theorem. So we can say, well, F3 then, magnitude, is going to be the square root of then F3x component squared plus F3y component squared. From Pythagorean theorem. Looking at my numbers for those, what I find is this works out to be about 282 newtons. So this is my magnitude. And then for the angle theta 3, remember we always use the arc or inverse cos or tangent, sorry, of then the y component, so F3y divided by the adjacent components, which in this case is the F3x. Now in this case, which quadrant should this be in? Is this the first quadrant, second quadrant, third quadrant, or fourth quadrant? First quadrant. So in this case, whatever my calculator gives me is the correct angle. And if I was in the second quadrant, in that case, my calculator would give me a fourth quadrant answer, so I'd have to add 180 degrees to that to move it over here. If I had it over here, in this case, if I was in the third quadrant, my calculator is going to give me a first quadrant answer, so I'd have to add 180 degrees to it. So I just have to modify from there. But in this case, since I'm in the first quadrant, I don't have to worry about that. So anyways, plug in my numbers, and what I find in this case then is this works out to be about 64.6 degrees. So this is the angle. Okay, not too bad. So again, the angles and things are all going to be basically based off of just the geometry. So in this case, since the forces is always along the line that connects the two, as long as I know this angle here, I also know this angle inside of here. So all of those angles will be dictated to me by the geometry of the problem. We'll do some more with these when we start talking about electric fields. That was okay? Any questions on those? Pretty straightforward, not too bad. So next thing we want to talk about is this idea that charged particles applied forces to each other over long distances. This long range force gave physicists a huge problem for a long time. This is what they used to call spooky action at a distance. So the pure fact that two things could interact with each other by some sort of spatial distance without being in direct contact with each other really bothered physicists. I mean, it's like really perplexed them. They had a real huge problem with this, but it was reality, so they just kind of moved on with it, right? Until eventually, what happened was what? Somebody proposed a resolution to this that made everybody happy. So physicists could actually sleep at night, they could go to bed, they could feel warm and fuzzy, life made sense, and everything was great. And this proposal was by a person by the name of Michael Faraday. This is the name we're going to see later when we start talking about magnetism. But anyways, what did Faraday propose? What Faraday proposed was that there was this thing that existed based off of charge. That charge created some sort of disturbance in space. This disturbance would then propagate throughout all of space. And then any other charge would then interact with the disturbance created by that first charge. And that's how the second charge would know about the first charge, because it felt the disturbance created by the first charge. This disturbance is what we call an electric field. So what Faraday proposed was that all charges generate a disturbance in space called the electric field, which permeates all space. Then the interaction between another charged particle and the electric field generates a force. So basically, the force that the second particle feels is by an interaction with the electric field created from the first. Right? So let's try to demonstrate and why we actually know that this is true. Okay? I'm not inside of the camera here, so it's over here. The world can see. There we go. So great. So basically, what I have here is in the first part, what I'm going to do is I'm going to turn this thing on. So what is this thing? This is what's known as a Van de Graaff generator. So basically, all this thing is there's a little motor in here that's going to spin. Around here, there's a felt cord or felt rope or ribbon, which is basically just going to get spun around by the motor. Inside of the globe here, there's literally basically just little like rakes, like a little rake inside of there that is going to strip off electrons from the ribbon. So it's going to create a static electricity. That static electricity then is going to fill this globe up here. Okay. So let's turn this guy off. Yeah. So you can kind of see the hair on here, right? So I turn it all the way down. If I turn it back up, this thing's kind of being pulled up a little bit due to the static electricity. Okay. So all this thing is doing is basically generating static electricity. I'm going to pull this guy up. Static electricity. Great. Now, what this thing is saying is, as this thing creates static electricity, it creates a charge, and that charge then creates an electric field that permeates through all space. Right? So, might be a little too bright in here, but let's see if we can actually see this. So what I'm going to do is I'm going to take that light bulb there. It's not going to be attached to any particular power source. And the only thing I'm going to do is I'm going to try to hold it near the globe. Like I said, it might be a little too bright in here. But what you should see, me shocking myself. There we go. It's kind of glowing a little bit near my hand, sometimes more than others. There we go. So what's happening inside of here is, again, there's no electricity. I don't have this connected to anything. But what's happening is the closer I get to it, the stronger the electric field becomes near the globe. In that case, what it's doing is it's actually then the electrons inside of the metal, inside of the light bulb here, are then being accelerated. And then as they're being accelerated due to the force that's being applied to them, they then create light. We'll talk about why this actually happens later. But you can actually then see the interaction then between these particular guys. Okay? So again, his resolution, which turns out to actually be true, is that this thing creates a charge. That charge then manifests itself as an electric field, which then permeates through all of space. And then the interaction between a charged particle, i.e. in this case, the electrons inside of the metal, then creates a force onto those guys, causing them to move due to the force, right? An acceleration. So this was his proposal. This made everybody happy. Turns out in reality that this is absolutely true. So win-win for everybody. Right? So this, of course, brings up some questions that we should be asking to ourselves. The first question is, well, what's a field? So we now know this thing is some sort of field, which is great. But what exactly is a field? So first way to talk about field is there's actually multiple different types of fields. The first type of field we're going to talk about is what's known as a scalar field. What's a scalar field? So the best way to think about a scalar field is something like this, which is a temperature map. So what I have here is a temperature map at some point in time of, for example, the United States. So what a scalar field is a scalar field is that every point along this space, there is a value. This is what a field is. So what a field is says that within any point within some sort of space, there is some particular value, which depends on the location within that space. Okay, this is what a field is. In this case, a scalar field. Why it's a scalar field is because there's no directional property to it, and it's temperature. So all this thing says is once I know the location I'm looking at based off the X and Y direction, let's say here, Evansville, Indiana, right? This thing says then I have a temperature of somewhere between 30 and 32 degrees Celsius. So this is what we call a scalar field. So a scalar field is, let's see, a value at every location in space, where the value depends on the location. So again, this thing is what we call a field. In this case, this is a temperature field. It's a temperature field because it's telling me the temperature at every given location within inside of the space. Another good example would be like an elevation, right? So an altitude. So how high is something? So think about mountains and hills and valleys and things. It's telling me the height that this thing is above. Now, this is a scalar field. Of course, the electric field is a little more complicated in the fact that this thing is actually what we call a vector field. So what's a vector field? So a vector field is something which has a value at every location and a direction at every location, which depends on the location. So it has both a value and a direction at every location in space. Which depends on the location. So this is what we call a vector field. So a vector field is something which has both a magnitude and a direction at every given location in space. A good way to picture this one would be, again, using our US. Think about a wind field or a wind map, for example. So in this case, if you think about the direction that the wind is blowing, at every location, the wind is blowing in a given direction. And it also has a magnitude, which would be what? The velocity of the wind. Okay. So for example, in this case, again, if I look at Indiana, in this case, Indiana looks like it is blowing in kind of the southwest, or what's that? Southeast, sorry, southeast direction. And it has a velocity, according to this, somewhere around 15 to 20 knots. Okay. So this would be a wind map, which would be a vector field. So again, has a magnitude in this case, which would be 15 to 20 knots, somewhere in that ballpark, has a direction, which then would be southeast. So this is what we call a vector field. So again, a field is anything which has a value at every location in space. A vector field is particular anything that has both a value and a direction at every location in space. So this quantity here that Faraday came up with, this electric field, is actually a vector field. So this thing has a value and a direction at every single point in space. This thing exists everywhere at the same time. All right. Now, how do we determine what the electric field looks like? Well, let's talk about that. So how do we determine what the electric field looks like. The way that we do this is we say, here is some region in space, and there's some pre-existing electric field inside of the space. Okay, it's going to be generated by something. I don't know what it is at the moment. I don't really care. Right? Now, what we're going to do is we're going to take something which is called a test charge. So we're going to say little q here is equal to what we call a test charge. So what I'm going to do is I'm going to take this test charge and I'm simply going to drop it into my space. So here's my test charge. Now, in this case, it's very particular. We have the test charge, which is going to be positive. So this is a positive test charge. Okay? Now, all I'm going to do is I'm going to watch how this test charge moves throughout the space. So let's say at this point, it's going to move through and it's going to do something like this. Okay? Now, at certain locations, what I'm going to do is I'm going to find what is the force on this particle at all these different locations. So at this point, let's say my force looks in this direction. At this point, my force is going to point off in this direction. Say at this point, my force is going to point in this direction. And let's say, I don't know, at this point, my force is pointing off in this direction. So at these different locations, I can then find what does my force look like. So both the magnitude and the direction. From here, we can then define what we call the electric field. So the electric field E, capital E, is equal to the limits as the charge of the test charge goes to 0 of the force per unit charge. This is what we call the electric field. Now, out of curiosity, has anybody in here taken calculus? Great. Now, this may scare you a little bit, because remember in calculus, whenever you see a limit as something on the bottom goes to 0, that usually means what? From calculus. A derivative, right? This is not actually a derivative. Okay, so don't be scared. This is not a derivative. All this means is, what this thing is saying is that we want the charge of the test charge to be so small that it doesn't interfere with the original configuration of the electric field. This is all this means. So it just means that I want to plop in this charge and I want it to be so small that the force onto whatever charged particle it was that's creating this electric field distribution doesn't push it away or move it around so it changes the electric field configuration. This is what we call back react. So basically this portion here just means that we don't want the charge Q to disrupt or change the original electric field. So no back reaction. So this is all this statement means. So again, it's not a derivative. Don't be scared about being a derivative or anything. All it means is that I want this charge to be so small that when I dump it in there, the original configuration doesn't move to change the overall electric field. All I want to do is I want to sample what the electric field is doing. Right? It's okay. Give you a good analogy. It's kind of like being a chocolate tester. You want to take one chocolate and try it, just make sure it's okay, not eat all of them. If it was my mother-in-law, they'd all be gone. Chocolate fanatic. My wife, she'd only take one. That's it. She's not a chocolate. Give her cakes and donuts and stuff, and forget about it. But anyways, should stop. So anyway, everyone's okay. So what does this thing mean? So what this means is I can find what the electric field looks like by simply knowing what the charge is at a given point, or not the charges, but the forces at a given point, and then simply removing that charge. So what the electric field tells me then is it tells me the amount of force a charged particle would feel if it was at that location. This is what the electric field tells me. So it's the force per unit charge. So it tells me how much force would a charged particle feel if it was at that given location in space. This is what the electric field is. So what that means is, in this case, if I was going to draw my electric field, my electric field then would point in the same direction as the force at that given point. Okay? Because in this case, since the test charge is positive, then these two have to be in the same direction since this guy is positive. Now it's also going to be bigger because the size of the charge is so small that if I pluck it out, I'm dividing by really small numbers, so that makes the electric field huge. Right? So in this case, my electric field then simply points in the same direction as the force at a given point, but the magnitude is going to be much, much bigger. So this is my electric field. Now, what are the units then of the electric field? Well, since this has units of newtons, this has units of coulombs. The electric field then has units of newtons per coulomb. So this is my unit of my electric field. So again, literally what the electric field is it's telling me how much force would a charged particle feel if it existed at a given point in space. This is what it tells me. This is what we call the electric field. But again, it's a vector field, meaning that it has a value and a direction at every single location in space. And if I want to know what the electric field is doing over here, I'm simply going to drop in my test particle at this point, watch how it moves, and then do the same thing over and over again. This is how we would determine what our electric field looks like in space. Now, before we get to I'll do this now. So since we now know that's what Coulomb's law, so let's think about what is then the electric field of a point charge. What is my electric field of a point charge? So to say that, let's use our Coulomb's law. So let's say I have a big charge here, which has a charge of capital Q. And then somewhere around here, I'm going to put in my test charge, where this is my test charge of little q. Coulomb's law then says that what? The force on little q by big Q is then equal to what? K times big Q times little q, all then divided by the distance r squared, where the distance r squared again is just the distance from center to center. So it's my distance r. Now, in this case, since they're both positive charges, what's going to be the direction of the force? Is it going to be repulsive or attractive? Repulsive. So I know the direction of my force is going to point off in this direction. This is my force, QQ. Now, let's say what I really want to know then is, but what is the electric field at this point? So what is the electric field at this point created by this electric field or this charge here? So using our new definition, what this says then is that our electric field at this point is going to be equal to the force FQQ, all divided simply by Q. So this thing says then that this is going to be K QQ divided by QR squared. What happens to those two little q's? That's all. So this guy's then going to be equal then to, let me write it this way, magnitudes, going to be equal to K Q divided by the distance r squared. What's up? Oh, that's a great question. You can't. What we could do is we could take something, not really a small particle, but I could take something kind of like this, where this thing only has charges which are allowed to move. So in this case, I would have charge separation since it's a metal, but it wouldn't be big enough to really push back onto this to move this, right? So in this case, what I would do is I would put this guy here with some sort of insulator here. And then what I would do is I would simply measure the amount of force on this guy and in what direction. And then I would physically move this guy over here and then do it again. Basically, yeah, so I can measure. So if I knew the charge of this one, right. Well, I mean, there would be a way. So for example, if I put, kind of like think about if I had a spring down here, right? Then I could think about, you know, if this thing was generating a torque, then how much force would I get from the torque down here? And then I would be allowed a way that I can measure the actual force between the two, and then I can measure the distance between them, and then I can find, just get rid of this amount of charge, and I can figure out the electric field from there. But as we talked about in lab, this is not really practically easy to do. This is why we generated, and we're going to talk about starting in 2 days, the electric potential. That's a lot easier to actually determine it that way, but we'll talk more about that later. But yeah, so in reality, this is not an easy thing to do. So that's why we don't actually really do it. But in principle, this is the way it would actually work, right? So good. So what this says then is that, well, this is then the electric field at this point from this particular charge. So it says the magnitude of the electric field at this point then is going to be kq divided by the distance r squared, where then the direction would be some radial direction away from it. So meaning that if I was at the same distance here, so this was my same distance of r. In this case, the magnitude would still be the same, but the direction then would be in this direction. Okay. Now that, of course, brings up the question of what happens if I have multiple point charges. So let's say I have point charge 1, Q1 here, Q2 here, Q3 here, let's say Q4 here. And I wanted to know at this point, let's call this point P, what is the electric field at point P? How do we do that? Well, in this case, if we want to know the electric field at point P, all we're going to do then is find, so let's call this R1, call this distance R2, this distance R3, this distance R4. And just for funsies, let's go ahead and make, I don't know. Lillian, you want Q1 to be positive or negative? Positive, great. Ryan, Q2, you want positive or negative? Positive. Jabin, Q3, positive or negative? Negative. Switch it up a little bit, great. And then Preston, you want Q4 to be positive or negative? Go positive. Okay. So in this case, at this point, all I would do would be do the same thing that we do with pairs with forces. So what I would do is I would calculate the electric field at point P from Q1, from Q2, from Q3, and then Q4. So I get something that looks like this. So my electric field in this case, E1 would point in this direction. E2 would point, say, in this direction. Since these are positive charges, it points radially away. This one would point in this direction. So this would be E4. And then E3 would then be towards, since he is negative. So this would be my E3. And then all we would do is then superimpose all of these guys on top of each other. So again, use our superposition principle to find the overall electric field at that point. So this would be, say, the direction of the electric field. So this would be EP. So mathematically, all this means then is that the electric field at point P would then be equal to the electric field from particle 1 at point P plus the electric field from particle 2 at point P plus the electric field from particle 3 at point P plus the electric field from particle 4 at point P, vector sum together to get all the directional properties associated with them. Or summation notation, this would then be the sum over I of EIP. Those would be it. So this would be what we call, again, the superposition. So the total electric field at some point in the space would simply be equal to the vector sum of all the electric field contributions at that point in space. Now, all of this also brings up a nice way to visualize an electric field before we do some examples of this, which is what's known as field lines. So let's start talking about field lines. So what are field lines, or in this case, more specifically, electric field lines? So electric field lines, or just field lines in general, are a nice way to visualize what an electric field would look like in a given space. So this is a visualization tool used to determine what an electric field would look like throughout space. So how does this work? So basically, this works in the fact that we say if we have a positive charge, so let's say here's my positive charge. What we now know is that what the electric field lines have to point away, since a positive test charge would be repelled away from the positive charge. So in that case, what we say is that what the electric field lines then originate on this positive charge and point away from it radially in all directions. This is what we would say is a positive charge. So this thing creates what we call a source. This is the source of an electric field. Now, simultaneously, I go back to my original picture. So this was Q, capital Q. And then this was my test charge of little q. And let's say little q in this case was actually negative. What would be the direction of the force on capital Q if capital Q was positive? Would it be an attractive force or repulsive force? An attractive force. So in this case, this guy would be attracted to capital Q. So this guy would go in this direction. Or if I made this guy positive and this guy negative, it would still be the same thing, right? It would be attracted to him. So this would be the direction of the force. So in this case, what we say then is that, well, negative charges then have electric field lines pointing inward towards them. So in this case, this would have electric field lines radially pointing towards the charge. Okay. Now, how is this useful to visualize an electric field? Now, what has to be true then is that what? The positive charge has to act as a source of electric field lines. The negative charge has to act as a sink for electric field lines, which means that I have positive charges and negative charges within inside of the same configuration. They have to originate on a positive charge and then terminate on a negative charge. Good example of that would be what we call a dipole. So the dipole is a positive charge and a negative charge. In this case, what we know is that, again, positive field lines are going to resonate or originate from the positive charge. Simultaneously, we know they have to terminate for the negative charge. So it's going to look something like this. Now, to then visualize what's happening throughout the space, all I then have to do is start connecting these lines together. So meaning that this electric field is actually throughout the space going to look something like this. This is my electric field. So in this case, I know they have to originate on the positive charges. They have to terminate on the negative charges, which means all I need to do is then connect these electric field lines together. And then this is what my electric field would look like throughout the space. Now, for these curved lines, all this means then is the direction of the electric field would point in the direction going from positive to negative. So this would be my electric field at any location along, say, this particular curve path. Okay. So electric field lines are a beautiful way of visualizing what this electric field is actually doing. Now, certain things to note about electric field lines is the density of the field lines. When the density of the field lines become greater, that means the strength of the electric field is bigger. Okay. So meaning out here, there's not a huge amount of density, so the electric field would be kind of small, but as I get closer in, the density gets larger because the field lines are coming closer together, which means the electric field would be getting stronger the closer I get to the charges, which means somewhere around here, since I have very low density, this would be a very small electric field out here compared to what's going on here. Now, how I draw this, again, if this had a charge of, say, 5Q, this had a charge of 5Q, then I'd want to draw the same number of electric field lines coming out of this one and into this one. But if this one had a charge of, say, like 10Q and this had a charge of 2Q, then I'd want to draw less field lines on this one than I would draw on this one, because the number of field lines would represent the strength of the electric field. But again, these electric field lines allow me a way to be able to visualize what the electric field itself is doing. Now, let's draw a couple of other examples, just to see how we would get used to this. So that's the dipole, but what would happen if I had, say, two positive charges? So let's say I put one positive charge here and one positive charge here. What would my electric field look like in this case? So let's draw a few electric field lines on each one. So I'll find electric field for him. Again, this is a positive charge. So his electric field lines have to point radially away as well. So what would this one look like? Well, this one, since this one is generating electric field lines, this one is also generating electric field lines. Where are my electric field lines going to terminate? At where? At infinity. That's right. So what has to happen is what? These ones can't go and connect to them. What has to happen is they have to actually come together, but they don't want to be near each other. So they're actually going to diverge away and only terminate by the time they get to infinity. Now, what has to happen is with any vector, I can't have two different vectors pointing in different directions at the same point. All that's going to happen is they're going to superimpose to each other and then point in the direction of the total vector between the two. Right? So ultimately what's going to happen is this one's going to go off something like this. This one's going to go off something like this. Right? This might go like that. Married way. This one's going to come down something like this, like that, and etc. So this is what my electric field would actually look like. So they'd have to diverge away from each other. So my electric field lines for positive charges would diverge away from each other, where for a positive charge and a negative charge, they would converge on top of each other. So they would end up bending inward. Now, one more example to talk about is what? What happens, or what does my electric field look like if I have an infinite sheet of charge? This will be important for things that we're going to do later. So we want to look at an infinite sheet of charge. So what do I mean by that? So let's say here's my sheet of charge, kind of drawing at an angle here, but this extends in all directions all the way out to infinity. And this chart is going to have some overall charge Q to it. So all I'm doing here is I'm saying this is my sheet. I'm just kind of drawing it like this, kind of an angle. I'm going to draw a side view of this as well. So let's say this is what it looks like. So this is kind of a skewed view. And then if I look at a side view, let's say this is my side view. So what happens in this case? So for this thing, especially on its side, what we imagine is that this thing is made up of basically an infinite number of test particles or charged particles, which are all basically just right next to each other. Right? So I can imagine this thing is just a line of an infinite number of particles, which are all next to each other. So let's go ahead and draw it. So what I can imagine is that's what? I got a whole bunch of positive charges, which are all just sitting next to each other. If this thing is positively charged, for example. So let's draw the electric field lines for a few of these. So let me draw, I don't know, this one here. So I'm going to put a line here, line like this, a line like this. Say this direction, this direction, this direction. Now I'm going to take another one. Let's say this one over here. I'm going to do the same thing. So I'm imagining each one of these has exactly the same amount of charge. So I'm going to draw exactly the same number of field lines. So these are all my field lines. But remember, every single one of these charges has exactly the same field lines. Right? Now let's think about what's going to happen. So if I superimpose this charge on top of this charge, what's going to happen? Well, what happened is these two are in the same direction, so they're just going to sum together. They're going to still point this way. But if I look at this electric field line here versus this electric field line here, so one is pointing like this, one's pointing like this, what's going to happen when I sum these two together? What would happen to the horizontal components? It's going to sum to zero, right? Because this one horizontally points this way, this one horizontally points this way. They're opposite direction. They're also equal in magnitude because they have exactly the same amount of charge. Which means when I add this guy here to this guy here, they also sum to only something which is vertical. Same thing when I sum this guy to this guy, the horizontal pieces are going to cancel, so I only have vertical components. So basically what's going to happen is if I had a sheet of charge, all of the horizontal components of the electric field would cancel, leaving only electric field which is perpendicular to the surface. So what happens in this case then is the total electric field then only points perpendicular or normal to the surface. So overall, this thing is going to have an electric field which points this way, at a 90-degree angle, and an electric field here pointing down in the opposite direction, also at a 90-degree angle. Now, what's really interesting about this, I'm going to write down this now, is it turns out that the magnitude of the electric field actually doesn't depend on the distance I am away from the sheet of charge. What it only depends on is what's known as the surface charge density. So it turns out the magnitude of this electric field turns out to be what we call sigma divided by twice of epsilon naught, where sigma is equal to the charge per unit area. So is what we call the surface charge density. So this is the surface charge density, which is the charge per unit area, divided then by twice of epsilon naught. Okay, so this is the electric field, any point above a infinite sheet of charge. But again, what's interesting is it doesn't depend on the actual height or how far I am away from the sheet. The value of the electric field is exactly the same. So on Blackboard, I put this guy here. So this is actually an electric field visualizer. So you can play with all kinds of different charge configurations. So here I have simply a negative charge, for example, which has -1 nanocoulomb, which is 10 to the -9 coulombs. So you can see in here, all the vector field lines are pointing inward. Or if I draw this as field lines themselves, again, in this case, these are what all the field lines look like. So again, this is radially away in all directions. So again, my figures up here, I can only draw 2-dimensional. But this is a full 3-dimensional where it points in every single direction. If I go back to the vector lines, if I switch this to a positive charge, oh, not density. I want reverse. Yeah. So now this is a positive charge. So again, now all of the arrows are pointing away from it. Okay. You can also play with some other stuff here. So we have point charges. We can do the dipole that we talked about. So this is what you look like here. So this is my positive charge. This is my negative charge. Or again, I can switch over to the field lines. Now that beautiful shape that we drew earlier. We can switch to other stuff too, which is known as a quadrupole. I can do something like this. All kinds of finite line, all kinds of cool little things in there. So these are, you can find these pretty much everywhere online. So different electric field visualizers, again, a nice way to see that your drawing matches exactly kind of what they have up here. So this is up on Blackboard, so you can play with this in your free time if you want to. Just for something. And again, you can switch this from positive charge to negative charge, and et cetera. Overstopped? That's a good question. I think there's got to be some simulations or something on here. Let's see. I think it's when you look at the particle velocity, it's doing something like this. But if I do stopped, it should pause it. Yeah, pause it. That's what it means in this case. So it's showing you if you had particles moving towards it, that would be the velocity at given points. Because then the acceleration gets bigger because the force gets bigger the closer you get to it. So the closer you get to it, they should be moving much more rapidly. So. Which you can kind of see. So here they're moving pretty quickly, and then out here they start slowing down. So it's okay. So this is electric field lines. So again, electric field lines are a great way to visualize what an electric field looks like. So that way you can kind of think about what this thing is actually doing. So next thing is, now that we know all this, let's start doing some examples. So all right, so first one is very similar to the first one we did the last time. So it says we have two particles fixed on the x-axis. The first particle, which has a charge of q1 equal to 8q, is at the origin. A second one, which has a charge of -3q, is located at a distance of x equals 3 to the right of the origin. What point, other than, again, spatial infinity, is the net electric field equal to 0? So this is very, very similar to the first problem we did on Friday. But again, let's draw our configuration. So let's say here is my x-axis. Right, here's my origin. So this is my y-axis. We're told Q1 exists at the origin. So here's Q1, where Q1 is equal to 8 times Q. Again, whatever Q is. Turns out Q won't matter. And then in this case, we know that what? Q2 is going to be sitting here. So Q2 is equal to -3 times Q. And again, we're told this is some distance of L away from the origin, which means these two are some L distance away. And what I want to know then is what? What place along this x-axis here is the total net electric field equal to 0? Is what we want. So where along the positive x-axis is the net electric field equal to 0? So we're just going to proceed like we did last time. We're going to split this thing up into, again, 3 different regions. We're going to region number 1, region number 2, and then region number 3. And we're going to do the same exact thing. We're going to argue for each one of these different regions and try to determine, could the net electric field be equal to 0 in region 1 or in region 2 or in region 3? Now, first thing what I'm going to do is I'm going to draw some electric field lines, though, only along the x direction. So here what I know is that what this is going to do something like this. Right, so electric field are going to point radially away for this guy. But since this guy is negative, this one's going to have electric field lines pointing inward. Now, again, these extend all the way to infinity, but again, the size of the magnitude is going to become different. I'm just going to draw those on there just for helpful visualization. So what? So what about region 1? Is it possible to have a net electric field equal to 0 in region 1? No, good, Logan, why? Q1 is just too big, and the distance from Q1 to the point compared to the distance between Q2 and that point is just too small. Right? So again, if we think about the electric field, again, our electric field magnitude is equal to KQ over R squared. Since here I have a large numerator divided by a very small denominator, that's then going to give me a huge number compared to this guy, which has a small numerator divided by a very large denominator, which is going to be just too small. Right? So again, if I was looking at some points, let's say this was my point of interest, what I know is that the electric field would point in this direction from E1. It would have to point towards E2 in this direction. So E2 would point this way, but the size of this field would always be bigger to the size of this field. So there's never any place where the two are going to be equal and opposites. They'll be opposites, but never equal. So good. So E1 is automatically gone. Or region 1, I should say. What about region 2? Also no, because in this place, E1 points to the right. E2 also points to the right. The two fields are in the same direction at all points, which means not possible. They'd have to be in opposite directions, but since they're never in opposite directions, it's not possible. So the only place it could be would be in region 3. And let's say that occurs at this point. So let's say this is our distance of x. And again, just to justify that, I know at this point here, since this is a positive charge, E1 then has to point to the right at this point. E3, since it is E2, since it's a negative charge, has to point in this direction. So E2 would point in this direction. And again, in this case, since even though Q1 has a bigger magnitude than Q2, but again, the distance from here to here is much smaller than the distance from here to here. So again, I can always find a place where these two ratios are exactly the same. So good. So the finite location, all we're going to say then is that the electric field at point P must be equal to 0, where this is my point P. Good. Using our superposition principle, we know this is then going to be equal to what? The sum of the two electric fields. So this is going to be simply E1 and E2. Now, in this case, since my positive x-axis points to the right, E1 is going to be positive, but E2 is going to be negative because it points in the negative x direction. Right? So I get a negative sign. Almost okay. In this case, now I'm going to apply this definition here. So it's going to be simply K times the magnitude of Q1 divided by the distance between these two, which is the distance x we just defined, it's going to be x squared, minus then k, magnitude of q2, all divided by the distance between these two. So what's this distance here? X minus L. Good. Those are going to be x minus L. I'll take these. Everybody's okay with that's x minus L? Because that's x, that's L, so that's x minus L. So good, same thing as last time. They both have a k and it's equal to 0. So let's just divide out the k because nobody cares. Equal to 0, so I'm going to add this guy to the other side. So I'm going to get a magnitude of q2 divided by x minus L quantity squared is equal to magnitude of q1 divided by x squared. Again, our job is to find out what x is. We're going to do the same thing as last time. How do you get rid of a square? Take a square root. So let's take a square root of both sides. Square roots and square roots. Now, again, I could factor it all out and have a quadratic to solve, but that's not fun. Let's do it the lazy version. So in this case, let's do that. So I get the square roots of the magnitude of q2 divided by x minus L is equal to the square root of the magnitude of q1 divided by x. Again, what I want is x. I'm going to cross multiply. So I get the square root of magnitude of q2 times x is equal to the square root of q1 times x minus the square root of q1 times L. Again, what I want is x, so I'm going to add the L term to this side and subtract the x term to this side. So I'm going to get a square root of q1 times L is then equal to, I'm going to factor out the x, so I get a square root of q1 minus the square root of magnitude of q2, all times x. And then finally, all I want is x. So I'm going to divide by that term and get it. So let's do that. So finally, I get x then is equal to the square root of q1 divided by the square root of q1 minus the square root of the magnitude of q2 all times L. Now again, both q1 and q2 have a q in it, so the q's are just going to cancel. So plug in our numbers. So this is the square root of 8 divided by the square root of 8 minus the square root of 3 all times L, whatever L happens to be. Look at my numbers. What I find in this case then is, lo and behold, it ends up to be exactly the same answer we found last time. 2.58 times L. Amazing. It was okay. Let's do another example. The next one is the second question, or second example last time, which is this example we started off today, except now what we want is we want to ignore Q3 here and find out what is the total electric field at this point instead of what is the force on Q3. Basically the same answer. We're going to stay with the same geometry. So basically we have the same thing, but we're just going to pretend that Q3 doesn't exist. So again, here's my y-axis, here's my x-axis. So now I only have the two charges. I got Q2 at the origin. I got Q1 at this location. Q1 was what, minus 86 microcoulombs. Q2 was 50 microcoulombs. Thank you. And then the distance between the two of those was 52 centimeters, if I remember correctly. Our point P, which I call point A here, but it doesn't matter. I'm just going to call it point P over here, is then 30 centimeters above him, which is then equal to 60 centimeters away from him at an angle of 30 degrees. So yeah, all I want to know is, at point P, what is the total electric field at point P? What's the total electric field at point P? This is one. Now, to do this, we're going to do very similar to what we did with the forces. We're going to draw first electric field lines. Right, so we need to know what does the electric field from these two charges look like at points P. I'm going to do basically the same thing as last time. So I'm going to say at points P, Q1 is a negative charge. So is my electric field point radially inward or radially outward from a negative charge? Inward. So at point P, all I'm going to do is say this guy has to point towards Q1. So this is my E1. And so it points along the line that connects the points to the charge. Now at point P, I'm going to draw Q2. Q2 then is what? A positive charge. So is it going to point radially away or radially inward? Away, right? So this guy's going to point in this direction. This is then going to be E2. Again, either using tip to tail method or the parallelogram method, whichever one is your favorite. The total field between the two is then going to point in this direction. So this is going to be my electric field at point P. Same thing as last time, I'm going to do the same thing. I'm going to move my origin to the location of point P. So I'm going to call this now my X direction. This is now going to be my Y direction. So this is going to be my angle theta P, and this is my angle theta, which again is equal to that 30 degrees, because that's what somebody told me in high school I should do. Okay. Amazing how you actually have useful things from high school. Okay. So now what I'm going to do is the same thing as last time. So since this is two-dimensional, what I'm going to do is I'm going to do the same thing. So I'm going to write the electric field component-wise. I'm going to look at the X components, and I'm going to look at the Y components. So anytime I have something which is two-dimensional or three-dimensional, this class two-dimensional, just automatically split it up into components. And I'm going to do the same thing as before. So what I want to do is look at, according to here, which one of these vectors has an X component? What is that X component? And then in the Y direction, I'm going to look at which one of these has a Y component and what's the Y component. So in this case, X component. Which one has an X component? E1, right? So this is then just going to be what? E1 X components. Based on what we talked about last time, since I want this portion of E1, this is the adjacent side of that angle. So this is going to be cosine. So I'm going to get an E1 cosine of theta. Now, again, this is a point charge, which means that we know the electric field then is going to be K times then the magnitude of the charge Q1, all divided by the distance, which in this case is this total distance here. This is my R1, so it's 0.6 meters squared, all times cosine of theta. Plug in a number as we find in this case then is this is going to be a big number. So this works out to be 1.86 times 10 to the 6th newtons per Coulomb. There we go. I could speak. Newtons per Coulomb. That was okay. Now let's look at the Y direction. How many vectors do I have in the Y direction? 2. Which ones? Oh, good. Which component of E2? All of it or part of it? All of it. So I'm going to get an E2. E1, all of it or part of it? Which part? Sign, positive or negative? Negative. Good. I'm going to get a negative E1 sine of theta. Good. From here, I'm just going to apply, again, Coulomb's law, which says that this is going to be K magnitude of Q2 divided by the distance between Q2 and the point, which is 30 centimeters. So that's 0.3 meters. Quantity squared, minus then K magnitude of Q1 divided by that distance, which is 0.6 meters squared, all times sine of the angle, sine of 30. Throwing my numbers for this guy, this works out to be 3.93 times 10 to the 6th newtons per Coulomb. Same thing as last time, I have now 2 components. I want to specify a vector, so I just have to find the magnitude of the vector and the angle. So let's go ahead and do that. So again, the magnitude is just by Pythagorean theorem, the X component squared plus the Y component squared square rooted. So I'm going to get an EP then, magnitude is the square root, EX squared, EPX I should say, there we go, plus EPY squared. Plug in my stuff, so this works out to be 4.34 times 10 to the 6th newtons per Coulomb. And then finally, the angle theta P is the inverse or arc tangent of the Y component at point P divided by the X component at point P, which lo and behold works out to be 64.6 degrees, exactly the same angle we had before. In this case, the angle is exactly the same as it was before because Q3 was a positive charge. Since Q3 was a positive charge, if I pull it out, that means the electric field has to point in the same direction as the force, right? Remember, our definition is that the electric field is the force per unit charge. So as long as this guy's positive, these two point in exactly the same direction. So since that was 64.6 degrees, this also has to be 64.6 degrees. The other way I could have found this is I could have simply took the magnitude of the force and divided simply by Q3, and I would have got exactly the same answer based off of this. So in this case, the magnitude of this is simply the magnitude of that divided by that. In this case, this would have been the force on 3 divided by Q3, which would have given me this, would have got the same answer, but that's fine. It's a good way to check, make sure what we did was correct. Let's do another example, whatever time we got left. We got 5 minutes. Let's see what we can get to. So this here says that in the figure below, 3 particles are fixed in place where Q1 here and Q2 here have both the charge of the fundamental charge. So that's little e, which as we talked about last time is 1.602 times 10 to the minus 19 coulombs. And then Q3, which is the charge of the origin, has double that amount of charge. Then it says the distance A, which is this distance here and this distance here, have a distance of 6 micrometers or micrometers. So I want to know at point P, what's the magnitude and the direction of the electric field due to these 3 particles? Okay, so let's draw this here. So here's my X and Y axis. So X and Y. I got charge here, Q1. I got charge here, Q2. And then finally I got a charge here, Q3, where Q1 is equal to Q2, which is equal to little e. And then Q3 is equal to twice of e. And then if I draw a dashed line here, a dashed line here, this is my point P. So my point P is at basically the center of a square, right? So if this was A, this is A. If I had another charge over here, this would be exactly the center of that square, right? Which would be correct. Now, there's 2 ways to do this problem. One way is what you would call brute force. So basically, you would just start finding out all the electric fields at point P and then simply just calculates and calculates and then eventually get to some points. The other way to do it is to think about it for a second and look at what we call symmetries. So anytime I give you a problem like this, and I'm going to give another one probably tomorrow, we'll start off with, what you want to do is go through and look at, is there anything that's going to cancel with something else? This is what we call a symmetry. So we want to see, are there some parts of electric fields which would automatically cancel with another one due to magnitude of the charges being the same, the distances being the same, and et cetera. Right. So in this problem, is there anything that would automatically cancel? Good. Which ones? Q1 and Q2, right? Because what I know is that both of these guys are positive charges. So what I know then is that what E1 would point in this direction, E2 would point in this direction. But how does this distance here compare to this distance here? They're the same. How does the charge here compare to the charge here? They're also the same, which means that the magnitudes of these 2 are the same, but these directions are opposite, which means that these 2 automatically cancel. So by symmetry, I know that E1 cancels E2, which means what's giving the only contribution to the electric field at point P? Q3. So that means that this guy, the only electric field I have at point P is that from the 3rd charge. That's it. Is okay? So in this case, what I know then is what? That the magnitude of the electric field at point P must then be equal to the magnitude of the electric field from charge 3. Now from Coulomb's law, what I know then is this is going to be K times the magnitude of Q3, all then divided by the distance, let's call that R3 squared. So what's R3? So R3 is going to be this distance here. This is my R3. So let's think about what R3 is. So again, I brought up the fact that this was actually a square. Right? So here's my square. I have A, and A. So this distance here is actually R3. Okay. Now, if this is A, what's this length across here? Across the diagonal. What's that? So hypotenuse, and particularly, how long is that compared to these ones? Good. So square root of a squared plus a squared. Well, what's a squared plus a squared? 2a squared. So it's the square root of 2a squared, which is the same thing as the square root of 2 times a. Absolutely. So this total distance across here, you draw that one in purple, is going to be the square root of 2 times a. That's the same as this distance here, but how much is this? Half of that, which means R3 then is going to be the square root of 2 divided by 2 times a. Good. So this is my R3. Is okay? Good. So let's plug this in. So this is then going to be equal then to K times twice of E, because that's the charge Q3, all divided by the square root of 2 over 2 A. Squared. Square root of 2 over 2 is the same thing as 1 over square root of 2. 1 over square root of 2 squared is what? 1/2, right? And then I have a 1 over 1/2, which means the 2 moves to the top. So this is finally going to be the same thing as 2 times K times 2 times E, all divided by A squared. Right? Plug in my numbers. This then works out to be what, 160.2 newtons per coulomb. So this is the magnitude. Now, I would have to now express the direction. Now, there's two ways I can express the direction. One is I can change my coordinate system, and I can actually call this my x-axis. I could do that. Be a little bit cheating, but I could do that. Or I can say, what's this angle here? 45, which means what's this angle here? 45. So then the angle is at what? 45 degrees. Oh, sorry, went 2 minutes over. So we have, I think, one more example. We'll do that tomorrow, and then we'll start talking about how electric fields play roles into conductors. So we know what conductors are. So what electric fields tell us about conductors, and then we'll talk about electric dipoles. I'll be here tomorrow, and I'll start giving you some group exercises tomorrow. It's okay. Person is taking it today, actually during lab, because they won't be here for lab. Probably by the end of the week. Because the other problem is we're hiring 2 new people. So basically today and tomorrow will be full of all kinds of interviews. So I don't know how much I'll get to it today and tomorrow. So, but it should hopefully be soon. Correct. We'll talk about that today. Okay. Any questions, Grant?
Just that. No, I'm all good.
Gotcha. Okay. I'll be recording anyway, so I'll send you a link. Okay, sounds good, Grant.
Thank you.
No problem. I'll send it to you in about 40 minutes. Okay.
All right, sounds good.
Right. See ya.
Right, bye-bye.